mathematical object, throw in some test particles, some light rays, some rods and clocks, and if they behave as you expect, right, if they follow the GD6 of the structure, if rods and clocks are locally behave like in special relativity, you'd say, okay, that's probably sufficient, maybe not necessary, but sufficient reason to say, well, we've a grip on what physical spacetime is in that theory. Right, so we're not the first to question whether there's such a rigid, right, whether stuff is either matter or spacetime. So here's a quote from Carlo Rovelli. He says, in the GR world picture, the spacetime versus matter distinction collapses. In GR, the metric or gravitational field has acquired most, if not all, the attributes that have characterized matter, as opposed to spacetime, from Descartes to Feynman. It satisfies differential equations, it carries energy and momentum, and in Leibnizian terms, it can act and also be acted upon, and so on, right? So many of the criteria you saw on the previous slide. And here it continues, even more dramatic. Since the discovery of GR, we no longer are sure of what spacetime is, and since the discovery of quantum, we no longer are sure of what matter is. The very distinction between spacetime and matter is likely to be ill-founded. We have learned so much about the world, but no longer know what matter, time, space, and causality are. And then finally, in the words of one of our co-authors, Niels Martens, one of the most important lessons of modern spacetime theory is that the distinction between matter and spacetime has become more and more blurred. Right, so what we've been doing in work prior to our project is look at a case study, well, a specific case study within dark matter, one that I think Aaron has also discussed 2 days ago at this event. So many physicists believe we need dark matter to account for many of the empirical phenomena. A much smaller group thinks, no, we can account for that data by modifying Newton's or Einsteinian gravity instead. And there's also a trend, it's a very small trend, but we find it as philosophers very conceptually interesting, between kind of hybrid theories, where you can kind of somehow get the best of both worlds, right? Somehow that, at least prima facie, looks like it's a little bit like dark matter and a little bit like modified gravity. And most of the examples we're looking at when I say gravity or spacetime, modified gravity, modified spacetime, these are two sides of the same coin, right? So you can say we're interested in the matter versus spacetime dichotomy or matter versus gravity dichotomy. Although I'll mention one case study later where actually it's good to distinguish those. But in most cases, modified gravity, modified spacetime, you can take them to be synonymous. So what we did in this work, in the 2 papers you see here with Dennis Leemkel, is we looked at this specific theory, one of the most popular ones on this list, called superfluid dark matter theory. And I'm putting the scare quotes here because the whole question is whether that is an apt name. But anyway, that was the name given to the theory by Lascia Bergiani and Justin Khoury. And well, what happens in that theory is that we get a phase transition. And of course, we're all familiar with the idea that substances can have different properties before and after a phase transition, right? So frozen water has the property that we can skate on it, as we were just discussing with Maria before, and liquid water doesn't have that property, right? So what happens in this theory is they postulate an additional field, and this field is very interesting because it naturally, right, behaves such that at large scales, it's a bit like an axionic dark matter field, right? All these the individual excitations, which look like dark matter particles, axionic dark matter. However, at small scales, and in this context, small means galaxies or the interior of galaxies, it behaves differently. Right? You get below a certain critical temperature, you get a superfluid Bose-Einstein condensate, you get massless bosons, phonons, which can mediate a long-range force. And if you choose the right kind of superfluid, this is exactly the force that the Mondians, right, the modified gravity people, advocate, and the one that tends to be relatively good at explaining the phenomena in galaxies. Right, so here we have a theory with, right, it's not a theory, if it would just be postulating 2 new fields, one is dark matter, one modified gravity, that's not particularly interesting, right? It's just both at the same time. But here we really have one field, which kind of is Janus-phased, right? It's dark matter-like at the large scale, and then modified gravity, modified spacetime-like, well, at least it seems, at the small scale. And indeed, what we do in detail in the paper, and I'm not going to focus on these details here, but the whole point of this talk is to give you kind of a flavor of the differences between the case study, the interesting themes, how the space-time-matter dichotomy breaks down in different ways in different cases. So lots of details in the papers if you want to look them up. But what we analyzed here is that, it satisfies not just energy, right? It has all the criteria of matter, this new field. It even has mass. So definitely 100% matter. We couldn't ask anything more of matter without losing the claim that even electrons, etc., are matter. But then at the same time, you can ask, okay, so what's going on with space-time? Right? If you throw test particles and light rays and rods and clocks into the center of a galaxy, will they see the standard Einstein metric or something else, right? Some construct, some combination of the Einstein metric in this phonon field, which here behaves as a superfluid Bose-Einstein condensate. And indeed, it turns out you can show that the test particles, they don't know there's the Einstein metric by itself. They only see this physical metric in the regime of galaxies, right? So we conclude that there's a sense in which it's also, at least in that regime, 100% modified gravity, modified spacetime, right? So conclusion of that first paper, this theory is 100% dark matter and also 100% in that regime, modified spacetime. So one of the upshots of this case study, we think, is that we think it would be good for the progress of cosmology and the practitioners there to kind of stop thinking about whenever there's a problem, like a dark matter problem, like, oh, it's got to be either a space-timey solution or gravity solution or a matter solution, right? In some cases, these solutions might clearly fall into that regime. But we really see, right, there's different communities associated with the different solutions. It's very black and white. But we think what this case study shows is that we should at least be open to the possibility that there is a single space of theories. And there might well be regions with pure spacetime theories or theories with objects that are purely spacetime and not matter. There might be regions that are pure matter theories, but there could well be, and we think we've given an example in the previous slide, of hybrid theories. Right, come to think of it, maybe we didn't even need this case study for that, because if you really think that something has to be either spacetime or matter, then what you should have expected is that there's one criterion, right? Either if you satisfy the criterion, something is matter, say, and if you violate it, it's spacetime. But we gave you two sets of criteria, right? Matter, spacetime, which at least on the face of it seem independent. I mean, I don't think they are, but on the face of it, they seem like that. So logically speaking, you should expect that there might be some things in the universe or in the mind of physicists, conceivably, which satisfies both sets of criteria, or maybe neither, right? Or just one or the other. Should at least logically speaking, be open to that possibility. And then as philosophers, where we think it gets interesting is, okay, so what now? What if we have this space of theories, which is much broader than we might have expected, with these hybrid theories? How do we navigate, right, such a much bigger space? And so what we did in the second paper with Leemkool is then provide a chart of various philosophical, conceptual, foundational interpretations you might adopt for such hybrid theories. And different hybrid theories might fit better with different interpretations, right? So I'm also not here trying to advocate one, like the absolute best interpretation for superfluid dark matter theory. The point is just to give you some examples which might inspire research into other case studies. Right, so either you might have kind of draw a very conservative lesson from this case study and say, well, nothing really changes. Okay, we have one example where something space-time and matter that doesn't change anything per se. Or you might take one of these fundamentalist interpretations, which I think connects somewhat to what Aaron will have discussed 2 days ago, where you say, well, okay, yes, in a way, it is fully dark matter and fully modified gravity, but it's like really importantly one and only derivatively, emergently, parasitically the other, right? And the name of the theory, superfluid dark matter theory, suggests, and I think that's also the case, that the creators of the theory think of it, and they also say this using the word, they say fundamentally it's dark matter and only emergently it's modified gravity. Of course, then you need, these are very loaded terms. People think of these terms in different ways, so then you need to spell out, well, what do you mean when you say fundamentally? Or you might, a more radical lesson you might draw from this hybrid theory or some other, or maybe a cluster of hybrid theory examples, is that the dichotomy breaks down in certain ways, right? And it could be because you think it becomes conventional, whether you call something space-time or matter, or maybe you learn from a case study that it's completely incoherent what these terms were, and you didn't realize it before. Or maybe you realized that you needed a third category, neither space-time nor matter. And what we do in the paper is point out, I think, superfluid dark matter theory is kind of an open research program. So as it stands, 5 of these are kind of viable, and some of the other ones definitely don't make sense for this case study, but they might make sense for other case studies. Okay, so that was kind of the longish prelude. And now in our project, we want to ask similar questions, but then for other case studies across astronomy and cosmology, because we think that the dichotomy breaks down, but differently in each case, which makes it particularly interesting for a philosopher. Right, so our case studies are an inflaton field, dark energy, black holes, and spin-2 gravity as compared to GR. And for each of these, we ask, well, for instance, the black hole, is a black hole matter, or is it a specific shape or structure of space-time, or is it both, or is it neither? Actually, today I want to focus on 3 of those 4 case studies. And this is not supposed to just be semantics, not just words, right? If there was all there was to it, then okay, well, I spent 5 years on it. But we do think that many of these questions and case studies have important implications also for model building in, say, the dark matter context, or generally in cosmology, but also for various old or less old debates in philosophy of physics, philosophy of science. Right, so for instance, substantialism relationism debate, which is all about is space-time fundamental or matter fundamental, but if you can't strictly distinguish these two, then maybe you can't even define this debate. Conventionalism is usually about, well, is the structure, right, Poincaré, etc., is the structure of the geometry objective or not? But here we'll see an example later, example where it becomes conventional just what the structure is, but whether some field or some structure is space-time or matter in the first place. And then also, this has interesting connections with the old scientific realism debate, right? Because if you come to me and say, I believe, say, in dark energy, and ask you, well, what is dark energy? And you can't even answer the most basic question, right? The first metaphysical categorization question you can ask, namely, is it space-time or matter, or maybe even the concept of nature, then have you really told me anything meaningful when you say you believe in that? If you said anything more than I believe in something. And then, as I said, the end part of the project is to develop a framework to help us navigate this new situation where we lost our old concepts, our old tools. Okay, so in the remainder, I want to focus on these case studies. And actually, what I want to do in the next few slides is focus on the first 2 together, but within the broader framework of scalar tensor theories. And very certain mainstream examples of inflation and dark energy are specific cases of this broad framework of scalar tensor theories. What I will say will be somewhat programmatic. I'm not going to give all the fine-grained arguments. You can find them in this archive preprint. But my aim here is really just to give you a gist of what's going on here, why this is interesting, why it's interesting, different from the other case studies. So what do we mean by scalar tensor theory? Basically, what you do there is you add to GR, so with its metric tensor, you add an additional scalar field which has certain properties, and most importantly, the last one, that the stress energy tensor and the dynamical equations for the matter fields depend only on those matter fields in the metric, but not on this new scalar field. Fine. Right, and then our main question here is, well, okay, we add a scalar field. Is this a matter field or a modification of the gravitational, of the space-time field, the space-time structure, or is it both, or is it neither? And the answer will be, it depends. Namely, it depends on the so-called frame. So, as is well known, scalar tensor theories can be written in different what's called frames, although it's perhaps a bit misleading term, so we prefer to call it representations of the theory. So one typical way is the Jordan frame. However, you can then get to what is called one of the Einstein frames via a conformal transformation. And typically think, well, if you're just doing conformal transformation, this is a change of variables, right? So under a standard notion of kind of how people think about symmetries, even though this is not per se symmetry, but how people think about changes of variables is just a change of description, doesn't change the physics. So if anything changes across these representations, there can be any need to it. They cannot correspond to anything in reality because it's just a change in description, right? And actually what we discuss in the paper is that also when you're in the Einstein frame or Einstein frame 1, you can kind of, change your variables again or rearrange the terms in the equations to get a different stress energy tensor. And this is what we call Einstein frame 2, right? And then we spent many, many pages on analyzing this, which I'm not going to bother you with. But the result is that if you use the categories of space-time and matter, what we talked about before, and you want to answer the question, the scalar field, is it space-time or matter or both or neither, then the answer will depend on the frame you're in. So in the Jordan frame, it turns out that the scalar field is quite pathological, or exotic. It's not what we're used to because it's neither does it satisfy space-time criteria or the matter criteria, right? So we have kind of a neutral field, or maybe we're missing a category and it should be the third category. And then in the Einstein frame, it really depends on how you define your energy tensor. Right? In one of the versions of the frame, the scalar field should be classified as space-time, but then in the other version of the frame, it should be classified as matter, right? So what we see here, if you just do a bit of changing variables, rearranging terms, you can get basically any kind of classification that you want. So if you think there's a real, right, if nature obeys space-time matter dichotomy in a black and white fashion, then this shouldn't be happening, right? So this might sound very negative. In the paper, we also have kind of a positive upshot, because then you can ask, well, if you actually kind of decouple your concept of gravity from that of space-time, then the scalar field actually does count as a gravitational field in all these frames, right? So you can say, well, if you want to hold on to an old category, the ones that we know and maybe love, gravity is the one to go for, but only if you divorce it from space-time. So that's the only category you can hold on to. So let me cash that conclusion out a bit more, right? So you can use the old interpretations we had and see how they apply here. If you want to avoid a conclusion, one first thing you might say is, okay, well, all these different frames give different verdicts, but maybe they're too fine-grained. Maybe there's really a kind of common core, something that's the same across all these frames, and that's the proper way to represent the theory. And that is maybe unambiguously, the common core might be unambiguously only space-time or only matter, right? And since you get between the frames via conformal transformation, you might think, oh, maybe the conformal structure, right? So the light cone structure, the causal structure, maybe that's all you need. Maybe if we only look at that, if we can get rid of all the other surplus structure and only leave that structure, maybe then our old categories are secure. However, that's not going to work. I mean, if there were only light in the theory, it would indeed follow the light cone structure, and light is not going to care which frame it is in. But all the other regular matter, right, all the matter fields we know and love that go on time like GD6, that conformal structure won't be enough, and they will be understood differently depending on the frame or the representation you use to describe them. So then what some people tend to go for is some kind of quietism, just kind of stamping your foot and saying, well, yeah, whatever. I don't really know how to phrase this view, because to us, this seems like flat out, right? It seems inconsistent to at the same time say, okay, there's a black and white dichotomy, space-time and matter, mutually exclusive categories. Here we have a theory where different frames give different verdicts. Okay, we're going to be quiet, and it's not really doesn't make sense to us, right? It seems if you, the theory, this kind of leads you to either saying, well, this is conventional, depends on your frame or your description, whether something is space-time or matter or neither, or maybe we used the wrong category, right? So, the wrong category. I'll get back to that in a second. Maybe you think instead we should go for the fundamentalist route, right? Maybe if you could argue, perhaps you think, well, maybe, yes, it seems like if you just look at the descriptions, you could use either the Jordan frame or one of the Einstein representations. But maybe one of them is fundamental and the other one is just parasitic, derivative, second rank. And of course, you have to spell out what you mean by those words. Or maybe you get even further. You might say, well, mathematically, formally, you seem to have both types of representation. but maybe one of them is pathological or doesn't represent the underlying physics, right? Maybe you really have good reason to favor one over the other. So we looked in the paper at what those reasons might be. The Jordan frame representation kind of naturally comes out of, for instance, string theory. On the other hand, Einstein frames have a feature that the scalar fields are not mixed, which you might think is a nice virtue to have. So then it seems we have a tie, right? One reason to favor the Jordan frame, one the Einstein frame. So maybe you think geodesic principle or energy conditions are going to break the tie. We looked into that, and it is much more, much less clear cut than you might have thought. So that doesn't just seem to be a clear way of privileging, right, metaphysically, fundamentally, one frame over the other. But even if you could, that would not solve the problem, right? Because our point wasn't only that how you categorize it, whether you categorize the scalar field, the space-time or matter depends on your frame. Within each frame itself, the space-time-matter dichotomy breaks down, right? In the Jordan frame, the scalar field is neither matter nor space-time, so it's neither container, neither contained. It's something else altogether. And in the Einstein frame, you can say the scalar field is matter or space-time, depending on how you define your stress energy tensor. So again, right, even if you would somehow manage to convince us that there's only one frame that's the real one, the physical one, you still have a breakdown of the dichotomy, right? So you think, well, maybe if you really want to hang on to these categories, you could say they're kind of conventional, they depend on your description. But to us, the most natural conclusion seems to be that space, time, and matter are just the wrong categories. They are not applicable. If you want to hold on to one, it's gravity, and we define it in a specific way in the paper, but then you need to decouple the notion of gravity from that of space-time, right? Yes, so I know this was a lot of information. I went over a lot of stuff pretty quick. All the details are in the paper. The point was just to point out that in scalar tensor theories, what's interesting there is that you have these different representations which shouldn't matter, but do play a big role in understanding whether space-time or matter apply or not. Okay, so then let me move on to another case study. Well, actually, I'm going to stay with dark energy, but now specifically dark energy, or even more specifically, the cosmological constant. And I'm now not going to talk about this broader framework of scalar tensor theories anymore. So dark energy is, well, in its broadest sense, the umbrella term for whatever is responsible for the observed accelerated expansion of our universe and the many different models. And the simplest one, of course, in our standard model of cosmology, lambda CDM, is that dark energy is a cosmological constant, lambda. And why is this case study, the cosmological constant, particularly interesting? Is because that we here get not just the dichotomy, but it seems like a trichotomy, right? You can ask, well, the base of it, you might think, well, lambda cosmological constant is just a constant of nature. But you might also have reason to think that it's a form of matter or a form of space-time, right? Because, for instance, we often talk about it as the intrinsic energy of space-time. So there in one go, you have intrinsic energy, right? Energy is the hallmark of being matter, but it's the energy of space-time. So they already have space-time. It's kind of a matter-like property of space-time, which at the same time is a constant of nature. What's going on there? And then relativists, right, if they talk about lambda solutions, right, solutions to the Einstein field equations with the lambda term, the cosmological constant term, but no T mu, no stress energy of the normal matter fields, they typically talk about it as a vacuum solution. So then it seems empty space-time, right? So you might think, well, lambda is at least space-time and perhaps also constant of nature, even if it weren't matter. What you can also do is absorb the lambda term into your stress energy tensor, right? Move to the right-hand side of the field equations. Then all of a sudden it seems like it's a lot like matter. And as we saw before, right, in the scalar tensor theories, you have this conventionalism. So it's another reason to doubt that this is a strict trichotomy or dichotomy. So this is already where you should hopefully not think it's obvious that lambda is only one of these three categories. But I want to make this point in a different way by trying to figure out what is appropriate explanatory narrative for explaining the accelerated expansion of our universe as we have observed it to be the case, right? And to understand that, one useful way is using the Raychaudhuri equation, which is this equation. a lot of terms, which I'll explain in detail. This will basically tell you the behavior of GD6 in the spacetime, right? Or if you have test particles on the GD6, it will tell you what happens to those. So let me first discuss these terms. And so the theta term will tell you whether test particles converge or diverge, right? So if you would start with a GD6 circle, by which I mean the circle of test particles, which are in this case all coming out of the screen or going into the screen, and then you can ask, well, at a later point in time, is the circle smaller or larger, right? Convergence, divergence. Right, so the theta parameter it tells you about the size of a circle of test particles, this geodesic circle. Then the shear term will tell you about the shape, right? Maybe when the test particles go through the space-time, they're kind of squeezed, right? Some of them are squeezed in this direction, the others in the other direction. And then finally you have the twist, right? The only thing left geometrically that geodesics could do that's not captured by the theta and sigma term is that it could twist, right? So even if, regardless of whether the circle changes size or gets squeezed, it could also be that maybe it doesn't do either, but the test particles rotate, right? We know the sign of the sigma term. In GR, typically in our universe, we believe the twist term to be 0. So if you want to know theta, what happened to theta, whether test particles or galaxies accelerate away from each other or not. Of course, in our universe, we have observed them to the accelerated expansion. Basically, you might be tempted to see this equation as everything here on the right side, which is the kind of which is the density and the pressure of matter things. They're kind of fighting with each other depending on the signs, and the sign that wins will tell you what the sign of theta is, right? Positive or negative will tell you whether galaxies on average will accelerate away from each other or not, right? And put like this, it seems very tempting to put lambda kind of in there with the pressure and the densities of the other matter and say, well, it's kind of a fight between all the matter stuff, including lambda, and whatever wins that fight, right? The energy and momentum, flux, etc. That wins will determine whether the universe expands or and in what fashion. So then it might well seem like we kind of have a matter explanation of what's going on, right? All the properties of matter, right, the density and the pressures will determine what happens to the geometry, the space-time, expanding or not. However, there are many ways of writing the Dichotomy equation. You could also capture all these last terms in this term, right, with the Ricci tensor. This is what Curiel calls the basic equation of gravitational attraction. And now it seems I've just given you pure geometry, right? I've just given you an equation which is only mentioning geometrical terms. So you might think, well, depending on the sign of this last term, the green term, the universe will, the GD6, the test particles will expand or not. So this is purely a geometrical story. So it seemed like we had a matter story of why the universe expands, but written like this, we have a geometry story. However, this story will only work if you impose an energy condition, right? The sign of theta dot will depend on the sign of this last term. And usually you determine that by imposing an energy condition, which the relevant energy condition here will tell you whether this term is positive or negative. And then you might say, wait, Niels, wait a second. You're saying, well, this looks a lot like geometry, but as soon as imposing the energy condition is the crucial premise, the crucial move in accounting for the accelerated expansion of the universe, well, energy conditions, I mean, energy, that's supposed to be, right, our buzzword for matter, right, our paradigmatic, the epitome of what it means to be matter. Well, that's tricky, right, how to think of these energy conditions. There are many of them. Here are 4 main classical ones, expressed here in the way Cantu and Sanders do it in terms of restrictions on, on the rho p, the density pressure space. And right, so here, we see the dark energy cosmology constant violates a strong energy condition, which is the relevant one here. But how to interpret these energy conditions, whether they indeed have a matter-like interpretation or a space-time interpretation, well, it depends on the energy condition. And the one that's relevant here is actually, you can interpret it in a matter way as a kind of effective density or effective gravitational mass, and also as a space-time interpretation, right, time-like convergence condition. So just to impose an energy condition by itself, at least this one, doesn't obviously make this a matter story or a space-time story, right? So the upshot here is, what I want to say here is that you can tell the story as a story of geometry, you can have it as a matter story, a matter explanation, a matter narrative of the accelerated expansion of the universe. The judge is out, right? Yeah. And then if you think that the gravitational explanation is in the spirit of, or goes hand in hand with, or bolsters, supports substantivalism, you might think that matter explanation bolsters or supports or relationism. Then the fact that you can tell this story in whatever way you want means that doesn't clearly advocate for either substantivalism or relationism for either of these stories, right? So the judge is out, and I don't see an obvious reason why this would change, right? Not like we're missing anything. It just seems like telling the story, you can do it in either way. There's no objective way of preferring one over the other, right? So much more to say about the dark energy case study, but I'll leave it here as far as that case study is concerned, right? So here, kind of for different reasons, for the reasons of how you interpret energy conditions, etc. It isn't obvious that one of these categories is the preferred one. So, okay, I have a little bit of time left, which is good because then we have one final shorter case study, black holes. And there, once again, the question is a black hole space-time or matter, or both or neither? And what we do here in the draft that's under review together with Son of Gouwen is ask, Schwarzschild black hole, right, the most simple black hole that we know, how to understand it, particularly look at its mass, right? So on the one hand, you might think, well, it has mass, right? This is parameter m, which is supposed to be a mass amount. That's what we're told in all the textbooks. You might think, well, mass, like if something is matter, I mean, if something has mass, it must be matter, right? That's the strongest criteria we have for being matter. At the same time, the Schwarzschild solution as a solution to the Einstein field equations is a vacuum solution. On the right-hand side of the field equations, T mu stress energy tensor is 0. So yes, there's an M here, but it's not an M that rolls out of any stress energy tensor. You might also say, what's a vacuum solution? It's empty space-time. So it seems like on the one hand, right, we say black holes, astronomers will tell you it's the most massive objects in the universe. You're like, well, it's the most extreme example of matter. But then from a relativist standpoint, it's a vacuum solution, empty space-time. So what we do in this paper is ask, well, why is this M parameter, especially if it's a vacuum solution, supposed to be mass? And we can think of a few possible reasons. Maybe you think, well, it has the right dimensions, end of story. Well, we think that's a bit too weak. You might think, as Dennis Lehmkuhl does, is, well, if you would only know GR, you couldn't really say that. But in the weak field regime, right, if you're far enough away, if you put a test particle far enough away from the black hole, then it will be as if it is, right, being attracted by a Newtonian planet with a mass that is numerically equivalent to this capital M in the Schwarzschild metric. Or you might think that, well, black holes, we can idealize them by zooming out and then replacing them with a point particle in Minkowski spacetime, because the Schwarzschild solution at infinity looks like flat spacetime. Right? You can pretend it's a point particle with a certain mass or a certain form momentum, which will give you a mass. Yeah. You might also say, well, there are many definitions of global masses in GR. The one applicable here is the ADM mass. The definition is there. Or you might think, as astronomers do, well, how do you build a black hole? You just have a collapse model. You collapse a lot of material stuff, right? Stuff that is, for which we know for sure it's matter, whether that's hippos or molecules, etc. Bring them together. That's how you create a black hole. Or maybe you think that the mass is somehow in the singularity, but then, of course, you have to tell us what exactly singularity is. Anyway, so, okay, so we think if you're trying to understand what the mass of a Schwarzschild black hole is, then you quickly realize that the space-time-matter dichotomy breaks down also in this context for a few reasons, right? One is this extensionally, black holes are examples, are a case that just satisfy both criteria, right? They have matter, so they are mass, but at the same time, right, you see here a vacuum space-time. So extensionally, they fall into both camps. But also intentionally, right, at the level of concepts, things get mixed, right? If you look at the global ADM mass, which is the favorite interpretation of the M parameter by the relativists. This is a limit of an integral which tells you how the metric behaves the further you move away from the black hole. And this is a purely geometrical condition, right? Mass itself as a concept is purely defined in terms of geometry. Right? The concept itself, right? It's not just you have separate criteria, separate definitions for space and matter. The matter criteria itself, you can't even define it without bringing in geometry. So also at that level, right? Extensional level, also extensional level, things get mixed, things get blurred. And beyond that, we think there's a sense in which it breaks down even more strongly. Right? You can ask for all of these interpretations. The relativists like to focus on the green one, but we think all of these capture some aspect of the mass of a black hole. And you can ask, well, on each of these interpretation, what metaphysics goes with that? What ontology goes with that? In particular, does it support relationism or standard substantivalism or super substantivalism, right? Where super substantivalism is the idea that only space-time is fundamental and matter is either identified with it or constructed out of it in some topological way or whatever. Somehow it comes out of the space-time. And what we see here is that for these different interpretations, we'll have different contradicting metaphysical verdicts, right? So the Newtonian trickle-down interpretation, if you think the only reason a black hole has mass is because far enough away from it, it resembles a Newtonian planet in the right way. This is in line with super substantivalism, right? It's kind of this matter property, it inherits from this limit. It's being pulled back down trickles down to the fundamental level, right? Fundamentally, it's space-time and then kind of gets this matter property via the limit. However, if you see it as if you idealize a black hole as a massive point particle in Minkowski spacetime, that seems to be the straight up substantivalism or maybe even relationalism. The global ADM mass does again seem to support super substantivalism, right? You just have a vacuum in spacetime, and it's the global structure of spacetime, right? This limiting integral of how the derivatives of the metric behave. That is what mass is. Mass is just a property that you need the whole spacetime, the structured whole spacetime defined as mass. Right? What makes it matter is a global aspect, right? Once you fix all the spacetime stuff, the matter aspect, the mass aspect is given. So this seems in line with super substantivalism. If you build a black hole by throwing hippos and elephants together, well, that's not super substantivalism. It's just straight up substantivalism or relationism, depending on how you think of elephants and hippos. And the singularities, again, a different interpretation. The point here is that if indeed all these interpretations of what the M parameter in the Schwarzschild metric is, if you think they all capture some aspect of what's going on in the Schwarzschild black hole, then they give you contradicting metaphysical pictures, right? And the reason for that is because they are holding on to, this whole debate holds on to, something's either space-time or not, space-time or matter. And then you can ask, is it fundamentally space-time relative? And then you get this metaphysical contradiction. But if you just give up on those categories altogether, the tension dissolves, right? So we think the most natural conclusion is not only is it that these kind of extensionally and at the level of concepts break down, just forget about these categories altogether. Just you run into problems. You don't need these categories anymore. If we never started with Newtonian physics and only a new GR, I don't think we necessarily needed space-time or matter, at least not as far as this, of course, very limited and idealized case study tells us. Okay, so that was mainly what I had to say. So I talked today about 3 case studies plus the pilot case study in dark matter. I hope to have shown you that space-time and matter, it's not a black and white issue. And then the rest of the project will further work on the philosophical implications and an overarching framework from where to go from now. There are many other case studies. Here are some of them. And we very much encourage you to use your own pet theory, your own pet case study, and join the research program and tell the community whether you think it is purely space-time or purely matter, or maybe it's another blurred example. And in fact, in 2027, our collected volume of our team, edited by our team, will come out, which does kind of exactly this. It's built up as follows. We have one part about definitions of matter, right? We have 4 chapters. We talk about, if you want to, what are we talking about when we talk about matter in the first place, right? As I told you, it's hard to figure out what people mean by that because it's supposed to be obvious. So here people will do the best they can to see if they can define the creator of being matter. Same for space-time, a few chapters on that. And then we'll move on to a long list of case studies, which most of them show, not all, that something, right? Something gray is going on, not black and white, right? We have inflation, black holes, dark energy, but also supergravity, etc. And then there will be a final part where I talk more about the conceptual level, like, well, is there maybe another concept we need? How does it connect to other distinctions we know from philosophy? Is there a tertium quid, a third category we need other than space-time matter or even gravity? And maybe that category is gauge, etc., etc. So yeah, let me finish there. I know this was a lot of information. The details can be found in the papers, or we can discuss this during Q&A. I wanted to give you a flavor of the kind of things we're doing. Thanks.
All right, so thank you, Niels. Let's react, give applauses and all this stuff. Well, so now we arrive at the time of Q&A. Please raise your hand in case you have a question, and I'll be moderating this. Okay, so we have Sergio first. Yeah, Sergio?
Yeah, thank you. Do you hear me well?
Yes.
Yeah.
Thank you. Thank you, Niels, for the keynote. I have just one question, and it is if you could state some philosophical implications of let's say the case in which matter and space-time merge. Would it change our whole conception of both or of some of them?
Well, what do you mean by merge? It really depends on the type of merging.
Yeah, by what I understood about the keynote, there are these cases where we cannot state it is just matter or it is just space-time, right? So one of the options where, well, maybe it is both. Maybe it is matter and space-time. I don't know if I understood well that. So that's what I mean by merge. I mean, if a phenomenon is matter and space-time, well, what would be the implications, the philosophical implications for the concept that we have of matter and space-time?
Yes, yeah, okay. Yeah, so the answer will really depend on your specific case study, right? So let me slide. Yes. Right, so some people would say, well, it doesn't have any, right? So those are conservative interpretations. They will say, well, it doesn't have any implications for the concept itself, right? So in the paper, we actually have lots of analogies. One of these is the consubstantiality interpretation of Jesus, where under that interpretation, Jesus is both divine and human, right? So you might have thought, oh, well, they're humans in the world and they're gods and that's it. But then actually we have one example, Jesus, which is both. Does this have any implication for the concepts? And well, if you have this one of these interpretations, you would say, well, this doesn't change anything. We still know from most humans that they're humans and not divine, and we know from the gods, except for Jesus, right? So it doesn't teach us it doesn't change anything about the concept of human or of the divine. And so under this interpretation, the same would apply to matter and space-time. Okay, we have found one case study where it's matter and space-time doesn't change anything about the concept. Now, there are more far-going interpretations, right? So the fundamentalist might say, well, it depends a bit which fundamentalist thing you might pick. So they might say, well, yeah, well, okay, so there again, you might say the concept doesn't change. It's just a question which of these concepts it's instantiated fundamentally. But we think, for instance, when it comes to the black hole case study, you can't even do that, right? It's much more radical than that. The whole, for instance, substantialism, relationism debate just becomes ill-defined. You can't even say anymore which one is more fundamental than the other. So then you come down to one of the breakdown interpretations, and there it depends which one you choose, and the answer will be different for different case study. So what we call the weak one, there you just say, well, space-time and matter are categories that don't really seem to do any explanatory work. If you want to keep using them, you won't be thrown into jail. You're not saying gibberish. You can do it, just there's no point to it. It's fine if you do it, there's no point to it. And these stronger interpretations would say, well, if it's like conventionalism in the scalar tensor theory, it'd say, well, you can say this, but it's just a matter of taste. You just represent, whether you represent something in polar coordinates or Cartesian coordinates, you can do one or the other. It doesn't, right? It's just your preferred way of looking at the world. It doesn't represent any metaphysics. So if you use space-time or matter, it's just a choice of words, just semantics, you're allowed to do it. If you think this is really inapplicable, and we think that is the correct interpretation of scalar tensor theory, then you say, well, these are really the wrong categories. You shouldn't use them at all. Gravity is, for instance, the category you might want to use, or Sylvester Borsbaum and Manus Fischer's thing. No, gauge, that is a separate category. You should be focusing on that. So it really, really depends on the case study, whether it affects the concepts or only the underlying metaphysics. Yeah.
Thank you very much.
Yeah, so if nobody has a question, I do have a question. And Niels, when I was reading your papers and this lecture, I think that some of the things that are motivating this research program is to increase the possibility space of alternatives, right? To solve all these anomalies at large scales and small scales. But I was wondering, yesterday we had a keynote regarding eliminative reasoning and all that stuff, and how can we choose between alternatives. In your own perspective, what are the correct criteria to choose between all these panoply of alternatives that we're having? Is it evidence? Is it its relationships with the current accepted theories of physics? How can we navigate this possibility space reliably? What would you say?
Okay. Interesting question. So yes, on the one hand, of course, what we're doing is naturalistic metaphysics, right? So very much doing the metaphysics and the conceptual analysis inspired by the physics. At the same time, what I'm more happy to do than perhaps some physicists is, right, so there's this book by Towards the Theory of Spacetime Theories by Dennis Leemkuhl and others, where they say, well, even if you would have only one path theory, let's say GR, right? Even if you would know certain GR is the correct theory of our universe, you can still learn something conceptually by looking at neighboring theories in the space of theories, right? Even if you would certain GR is correct, you might still want to understand what is special about GR. So you can ask strong equivalence principle, Einstein equivalence principle, etc. Do all theories have that near GR? Only GR? Does all these theories have it? It's not special about GR. If only GR, it's special. So, so in that sense, I mean, evidence. Yeah, so in that sense, we go beyond empirical adequacy and also look at neighboring theories. So in that sense, we go beyond evidence. Of course, for instance, when it comes to superfluid dark matter theory, if the first version got into problem because of the LIGO results, then you see people work on these theories playing around with it, right? So first you might have coupled everything to this, not the Einstein metric, but the Einstein plus phonon metric. But then you get the LIGO results, and then there are new theories where maybe photons are coupled in different ways, and they're like, oh, this is conceptually interesting because now maybe there are two spacetimes. That sounds weird. So maybe there's no spacetime whatsoever. So sometimes the empirical progress provides us with inspiration. Sometimes if we're not empirically forced to look at a neighboring theory or modifying the theory, we do it anyway to see if that would change anything or not, and thereby learning what's going on. So yeah, a mix of both, but of evidence and conceptual analysis.
Yeah, it's just a picky question. How would you frame this research program? Is this that we need more criteria to distinguish between space, time, and matter, or is it that we might just simply be facing a sort of scenario where these two concepts have to be taken together, such as it was with the electric field and magnetic field? Just to frame that, it's just a clarifying question.
Yeah, the second option.
Yeah, perfect. Right. So now we have Niels Saavedra question. I'm going to read it to you, but it's also in the chat. And it says, does your team have an interest to approach in the future or of some kind of cosmological singularity problems under those terms of breaking the matter space-time dichotomy?
You mean specifically like the Big Bang, or as opposed to black holes?
I think so.
Good question. Well, we are not planning to focus on it in the next 10 years. Sorry, 2 years. But yeah. So we aren't, but that shouldn't stop others from. It might be an interesting case study. So, yeah.
Right. Well, now we have a Facebook question. It is also in the chat. I'm going to read it to you. And it says, you seem to have argued that abandoning the space-time-matter dichotomy is increasingly well motivated by contemporary cosmology. But how should we tell whether this is an ontological lesson about what exists, rather than a methodological or representational shift driven by current theoretical practices? In other words, what would count as evidence that the dichotomy itself, rather than our models, has broken down?
Okay. Yeah, well, I think maybe the dark energy or the cosmological constant case study is relevant here, right? Because the point there is, especially the first slide I had on that, is these models are always kind of, because it's right, dark energy, there's an energy there, but it also somehow needs to connect to the lambda term in the field equations. It seems like it's always going to have some of these aspects. So whatever. Okay, it might not be a constant of nature, of course, if it's not lambda, but something else. But all these kind of things are always going on there at the same time. So I would be very surprised even if we find our final theory, that all of the hints we pointed out are going away, right? We're kind of saying the opposite. Well, yeah, we probably don't have the final story, but all the hints we discussed are telling us that you might well have to look exactly in the hybrid regions, in the gray regions. So yeah, I would find it hard to imagine that there's going to be some final story which somehow reintroduces this dichotomy in a black and white manner. Yeah, but maybe I'm missing something there, but yeah, I can't think of it.
Right, so now we have a second Facebook question that says, thanks for the very interesting talk. If space-time-matter distinctions are being relaxed or dissolved across different cosmological frameworks, how do we avoid increasing underdetermination at the level of ontology? Does giving up the dichotomy risk making competing theories harder to compare, or do you see it as introducing new, more discriminating criteria for theory choice?
Well, I don't think it's gonna. I mean, I'm not really thinking of this research program in terms of theory choice, other than making practitioners in both cosmology and philosophy aware of, oh, maybe we are overlooking hybrid options. But in terms of underdetermination, right? Supposedly there's underdetermination in some cases because there's either the space-time option or the matter option. But our whole point is, well, you're just making a distinction that metaphysically doesn't really make a lot of sense. So I would say, well, if it's going to change the underdetermination at all, it's going to make it better because it's going to get rid of distinctions that don't need to be there at all. Yeah.
Right. So, anyone in the audience wants to ask Niels something?
There is a third question also from Facebook on chat.
Yeah, I haven't just seen it. Third question. I wonder more about the metaphysical consequences of the project. If the space-time-matter dichotomy dissolves, do traditional debates like substantivalism versus relationalism generally become moot, or do they simply reappear at a different structural level, say in debates about fields, topology, or dynamics?
Interesting. Yeah, so I think it depends a bit. So unfortunately, I couldn't be at Aaron's talk, but he will write a chapter for a collected volume, so I'll definitely get to read the details. Right, so I think it was all about supersubstantivalism. So in some sense, I think, correct me, Aaron, if I'm wrong, at least perhaps in a modified form, that debate lives on. Yeah, again, it really depends on the case study, right? Our whole point is that this research program is interesting because there's not just one correct philosophical interpretation for everything. There's different cases will give you a different story. So, for instance, for the scalar tensor theories, I find it hard to know what it would even mean to still define the substantialist and relationist positions if you don't have can't objectively say whether the scalar field is matter or space-time, right? Are they going to say, is the scalar field conventionally understood as matter, metaphysically fundamental relative to the scalar field understood conventionally as being so I wouldn't really know how in those cases. I mean, there will be some case studies where it's not so radical, it will remain. Other case studies, and we think in the black hole case study, for instance, it just creates problems, contradictions. So better get rid of the categories. Yeah.
Perfect. We have a YouTube question, but before that, I want to make my own question. Today, Aaron was giving his talk. He mentioned that these superfluid dark matter had some ad hoc component that would make it like dubious, like it had no real motivations, like you could be suspicious about it. And my own intuition is that this whole space of possibilities that attempt to resolve all these anomalies at the observational level take some ad hoc, take some things ad hoc, right? Some things are not consciously motivated. I was wondering, what do you think that is the reason that we have so much ad hoc alternatives? Is it because we are extending our theories much more than we should be? Or is it that maybe it is just the way science progresses? Maybe we should be relaxing this ad hoc condition on trying to think what is rational for pursuit or not rational. I don't know. I do not know whether you know about this paper from Durer and Wolf, where they compare Mond and dark matter, and they say that modified gravity is much more ad hoc than dark matter, and that doesn't make, for me, much sense. I don't know. What do you think about these discussions regarding the ad hoc modifications?
Mm-hmm. Yes. I find it in general quite interesting that different camps, for instance, dark matter modified gravity camps, have very different intuitions about what counts as ad hoc or not, and it seems very hard to find to find no objective answer there. But when it comes to superfluid dark matter theory, I think there's one sense in which it is ad hoc, and in one sense it isn't. So the sense in which it's not ad hoc is that when you have other hybrid theories, but hybrid theories, where they just add two new fields, right? Or some weird mechanism where this one field all of a sudden becomes something else. That's not what happens in superfluid dark matter theory, right? You have one field, and because it's a boson, like an axion, at some point it's going to condensate, right? So the only thing is, are your parameters right such that it happens in the galaxy, right? That will happen. It's unavoidable. So in that sense, it's not something extra. It's more you should ask people who don't use hybrid theories but still use the kind of bosonic dark matter options. Like, have you ever thought about that? I mean, you cannot not. It might just be that it's not relevant or in the wrong regime, but so it's unavoidable. So in that sense, it's not ad hoc. But it is. Well, I don't want to use the word ad hoc, but how you just described what Aaron said, it is definitely phenomenological, and there's no full fundamental theory with all the top-down symmetries in the right way. Yeah, I mean, I'm not that just. I mean, it's not that old in theory. I'm not that surprised. You got to start from somewhere. Maybe eventually find some top-down approach. Right. My point here is not that I'm advocating that superfluid dark matter theory is the correct theory of our universe. I think it's conceptually interesting, and different versions of that theory are also conceptually different because they will think differently about what space-time is or not, right? If you couple the photons in different ways, you get maybe more space-times, or show that it also doesn't make sense to think about space-time anymore at all. So that was really more my point. Like, oh, there's this conceptual opening that people are overlooking because they're using either their dark matter goggles or modified gravity goggles, and there's a lot of groupthink within their communities. So my point is not like, oh, we should now all go away from this talk thinking superfluid dark matter theory, that is the correct theory of our universe. It's just such hybrid theories are conceptually interesting, and maybe a different hybrid theory is the way to go.
Right. So we have the fortune that Aaron is here, and I think he may want to press you. But we have first the YouTube question, so maybe you can go quick on it. The question is, many of the pressures you mentioned, dark matter, dark energy, inflations, are themselves deeply theory-laden. How do we disentangle whether the breakdowns of space-time matter distinction is driven by empirical anomalies, by theoretical unification goals, or by metaphysical dissatisfaction with older conceptual schemes?
To be honest, I'm not sure I have more to say than the answer to your question, Andres. It's the empirical anomalies inspire what we are doing in this research program, but I don't think to make interesting what we're doing, we need to only look at theories where I think they stand a very good chance of being the correct theory. So yeah, I would just repeat what I said earlier. I'm gonna keep going.
Right. So now we have Aaron.
Yeah, hi Niels.
Hello.
Thanks so much for your talk. No, I just have this question that again it is a case that I raised in my speech, and I would like to know about your opinion, about it.
Sorry, I was ill, so I haven't responded to your email and couldn't be at your talk. Sorry for that, but yeah.
No problem at all. No. My point is this. It's just a quick question. Just consider a simple universe, a stupid universe with just a river which is flowing in this space-time, and a leaf on it, which is just, it is following the flow of the river. And in a sort of way, we can describe the motion of the leaf by, in a sort of way, defining an effective metric that defines the causal structure of the space-time perceived by this leaf. So I just wanted to know whether you consider this as a case of modification of space-time or not.
Yeah. I think not in those words, but talked about it a little bit in the second paper with Leemkool, so I mean, I see what you're getting at that example. I think that this analogy is that for the Bose-Einstein condensate, right? Some people who do philosophy of phonons, etc., talk about phonons and crystals, and that is like similar to the water, because you could say, okay, forget about that. There's more to say there. But in the superfluid case, right, the whole point is if it's really a Bose-Einstein condensate, then you can't really talk about individual particles anymore, right? So only if you start from the high temperature level and think, oh, they're particles, and then somehow they are hidden there. But if you start from low temperature, like, no, the only correct way of describing it is this collective thing. I mean, collective is even wrong because it suggests there is kind of a sum of different things. But no, there's only, right? It's not even, you can't talk about, there's no underlying stuff. Fundamentally, that is just what's there. And then only particles appear at a higher state. But so they are. So I would say that's this analogy with the water case, where we'd say, well, the water case, we know there's a fundamental underlying theory based on the water molecules, but I think for Bose-Einstein condensate, that's not the case.
Yeah, that's exactly the case I'm raising. Okay. Thanks so much for your answer. Okay.
Yeah.
Perfect. Well, so I think this is the perfect time to stop. And now, thank you, Niels. We can now go with the first contribution speaker, the first contribution talk, which is Mariana's. Mariana, are you there? Yeah.
Yes.
Excellent.
Hello. Hi. Okay, I'm going to start. Okay. Sorry, my computer is acting weird. Okay. Can you see the screen?
Yeah, but we can also see your browser. Can you make it like in a full screen mode?
Okay, so I tried that earlier and it logged me out of Zoom. So I'm scared that it will do that now. Okay, I'll try staying it like this if that's okay, just so that it's not, it doesn't let me out.
Move in one slide so we can make sure it moves accordingly. Sometimes it moves slower
Okay.
that it moves in your computer. So we are now seeing, we were seeing James Webb Space Telescope. Is that the same thing you were?
Good. Yes, it's okay. Hopefully that's okay. Okay, so hello, my name is Mariana Cerca. I'm a master's student in philosophy of science. My background is in philosophy, so I hope that you don't judge that I don't know, like I'm not a specialist in cosmology. So I'm open to you guys telling me if there's something that I should know about. I'm writing my master's thesis on philosophy of science and epistemology and epistemic capacity of big data. And I was curious to see how this will translate in cosmology and the phenomenology of cosmology. So, okay, I will start. So 2 years ago, the James Webb Space Telescope sent back images of massive, fully formed galaxies that existed just a few 100 million years after the Big Bang. The problem is that these shouldn't exist according to our lambda standard model because there wasn't enough time. And when scientists first saw the data, many of them assumed that it was noise or dust or like an error in the system. And they tried to force it to fit the model so that we could read it in a different way. The problem is that if our data pipelines had been more aggressive in filtering outliers, we might have deleted and ignored these galaxies entirely. We wouldn't have known that they existed or how they worked. And the only reason that we understand their existence today is that we analyze the error and intervene in the system to save the outliers. However, this case led us to question the types of problems that we could face now because we start using more generative AI and epistemic capacity as data to measure and observe the cosmos with new instruments. In an age of petabyte scale cosmology, how many anomalies might we already have deleted? How much of the actual universe might have we filtered out because we didn't fit our algorithm expectations? Mostly it affects algorithm when it detects a pattern in the cosmic microwave background that no human could ever see. So how do we call this? Is it still an observation, or is it just data that we gather and observe after? How reliable can it be? I want to argue that now that we have crossed that threshold, we're no longer doing cosmology in the traditional sense, that we have moved from observation of the cosmos to computing of it, and that this shift has to change how we think about scientific observation and the justification of it. So first, I want to start with the distributed observer. So telescopes like the Elucid satellite or the Vera C Rubin Observatory produce massive noisy databases. It's a lot of terabytes of raw information. And certain algorithms have already decided what is a signal and what is noise based on parameters we programmed ourselves. Before a photon from a distant cursor reaches our eyes, it passes through a gauntlet and hits the sensors, and it then is digitalized. So we're not interacting with anything of the cosmos itself. We're interacting with a version of it that is already digested, and we understand it through the computational way. We don't see it directly. This creates what we might call an epistemic predicament, to use the term from Duran for Marshek work on epistemic opacity. So this means that we have displaced the center of knowledge production. So like I put a little cat in a box, like Schrodinger's cat paradoxy. So basically we don't know what is going on inside the database, and we only see what it shows us. So like all the pixels that is already digested, and that we are left to figure out and to interpret in any way, but we can't really see them, like, because it's in the cosmos. So because in a science like cosmology, we have to make a lot of assumptions. We assume our instruments are working correctly, even we cannot physically verify the electronic states of every sensor. And so we trust the black box of data. And we trust that it will detect those patterns for us, and that it will tell us what is wrong and what is good, or like what it can be interesting for us to study more. We call this the distributed observation, which means that the observer is no longer the scientist himself, as it has been historically, but is a network. So the observer that stays in this state to see the cosmology, the data of cosmology, is a database, a big database that we no longer control or observe ourselves. We're just in the state of the consumer of the network, and sometimes we can be the interpreter. So in this way, we build a black box cosmology, like I said, and the why ends up disappearing. We get the prediction right, but we lose the causal chain, and we're moving from an epistemology of understanding, so like why does gravity work this way, to an epistemology of how does the output map the distribution kind of way. The problem is that our algorithms work only based on what we already know. And we train them on our current cosmology, specifically the standard model, or lambda called dark matter. So again, if the universe contains a phenomenon that behaves in a way our mathematical models cannot predict, the algorithm might filter it as error before we ever see it or understand it or intend to interpret it. So we end up missing information because we aren't experiencing it firsthand, and we are experiencing a model of it. So in this way, we end up in like a oracle science, where we let these systems interpret the cosmos and interpret the data that it's sent to them, and we're only left with these interpretations. So we have to understand them already digested. Because if the machine has no concept of anomaly, it only sees statistical regularities. So we only see like a mirror that reflects the information that is going through them. This is illustrated by Marie Gouwen, in this article that I put here. By the scientific obsession over robustness, when 10 different imagining pipelines using 10 different algorithms all return the same result. And they are early because we say, okay, the result is robust, so it must be true. But in her paper, she points out a logical trap where she argues that robustness is only valuable if the lines of evidence are truly independent. But in modern cosmology, they are not. If we run 10 simulations and every single one of them shares the same core of assumptions, say they all enforce general relativity, or they all rely on the standard model, lambda CDM, their convergence is not proof of truth. It is merely proof of a shared bias. So if they all say that one thing works one way, it doesn't necessarily mean that it's true. It could also just mean that they are all programmed the same way. So if every model is built on the same mathematical codec, then they are not discovering the universe. We're just agreeing with each other and auto-justifying our science facts. If our robustness is just an echo chamber, then the anomalies, like those massive early galaxies that we found in GWST, they are not the problem, they are the solution. They are only pixels that did not fit the compression algorithms. So when our data pipelines feel like these galaxies as noise, they aren't detecting a mistake of the universe, they're detecting the failure of our shared assumptions. To further explain this, the philosopher and computer scientist Judy Pearl distinguish before seeing, association, doing, intervention, and imagining, counterfactuals. He calls this the ladder of causation. Current big data AI is stuck on the first rung, which is association. It sees patterns, it sees galaxies' rotation curves flatten, it creates a curve fit, but physicists and cosmologists require the third rung, which is counterfactuals. To prove general reality, for example, Einstein didn't just find a curve to Mercury orbit. He began asking if gravity were not a force, but a curvature of spacetime, what would happen to light passing the sun? This is a counterfactual. And we can also see this with Kuhn, for example, who had already talked about what the core values of science are. So he has different types of values of science. In one of them, the most important one is that it has to be refutable. So that means that we have to be able to criticize it and have contra arguments for it. But this is not the case for cosmology, because a lot of the big data that we use to gather information already analyzes this information for us. So it's another way in which we can no longer consider it as a classical science. For example, a neural network can predict the location of a galaxy with a 99% accuracy, but we cannot ask it why it's there or what would happen if gravitational velocity changed by 1%. It has no answer and no theory, and it has no concept of why. And so this leads to the main question, which is, when the tool shapes the observation, how do we separate the cosmos from the code? And how much of it becomes scientific knowledge versus how much of it is scientific justification? Okay. So now I'm going to talk a little bit about phenomenology, because if we translate this into phenomenological terms, this means that we have displaced the subject and the mode of access is the object. So I can only access a gravitational wave through a specific computational pipeline that subtracts terrestrial noise. And the object is the output of that code. So for a long time, phenomenology, especially in the tradition by Husserl, rested on a confronting concept, which was the life world or Lebenswelt. This means that the lived world, the ground from in the world of our immediate experience, is what we know for sure. So, for example, if we have a cup in our hand, or a chair or a wall, we know that it exists because we are perceiving it firsthand. However, cosmology forces us to confront the terrifying reality that we are studying entities that cannot enter a human life world. So there's no phenomenological experience of it. Whereas most phenomenological analysis of scientific practices presuppose that instruments serve to extend perception towards a pre-given life world, cosmology fundamentally ruptures this assumption. So the object it addresses, quasars, supermassive black holes, or the cosmic microwave background, are ontologically uninhabitable, spatially non-local, and temporally inaccessible to the human sensory. This necessitates a profound revision of phenomenology itself, compelling us to reconceptualize our relationship to the concepts we study, as we cannot ever experience them through our direct intuition. So it's a whole different type of science, because we can't verify it through our initial primitive senses, and we cannot study a classical phenomenology of it if it's not, because it's not something that we can experience. Okay. So this can make us question what AI can do for cosmology and for the cosmology science, and the way that we use big data with it. The prevailing naive realism, which posits that objects are out there awaiting discovery, is challenged by the work of Marie Gouin that we mentioned earlier, because she argues that scientific knowledge is not merely given, but constituted. They come into being solely through the specific modes of access we employ. Historically, this access has visual or tactile, but in digital cosmology, the mode of access is a computational pipeline. So a galaxy is no longer simply a traveling string of gas, but it's a partner of pixels that have survived calibration algorithm. Contemporary cosmology studies entities that appear only through these complex epistemic chains, but one cannot encounter a gravitational wave directly. we can only encounter the data output of LIGO after it has been filtered against terrestrial noise. So the object in the signal that survives the process, and data infrastructures do not merely extend our senses, but they constitute the conditions of experience themselves. So work on the philosophy of observation by Lorraine Aston suggests that what counts as observation in modern science is inexplicably shaped by the epistemic apparatus. So we no longer interact with what we're studying, but we only interact with the data that comes from it. Rather than immediate sensory perception, we only have epistemic apparatus. We are witnessing an acceleration of this process because recent projects employing neural networks to identify strong gravitational lenses are detecting objects that human observers systemically miss. Emergent AI foundation models such as Google GraphCats or specialized astronomical models are now capable of discovering patterns autonomously without being instructed what to seek. Regarding prediction, we are witnessing a shift, so we go from prediction to generation in science, especially in cosmology. AI are effectively hallucinating potential universes or situations that we could study in science. So when AI isolates a pattern, sometimes if not most, we cannot comprehend the mathematical operating within its brain, which comes back to the black box problem. So we end up confronting a big question, which is how can we maintain the nomenclature of science for a process we no longer understand? Like, how can we invest in the algorithms agency and trust it to be able to study the cosmos or any science in a way that we can understand it? If our access to reality is fundamentally data-driven, then where does the event of discovery transpire? Increasingly, it transpires inside simulations. We have historically conceived simulations as representations. So this is how we try to understand this data that comes from the observations that these computers or these systems do for us. And we simulate different universes, for example. But they function more accurately as epistemic environments or exploratory spaces. So they're not really data that we can understand. For example, the Illustrator simulation does not only generate a pictorial representation of the universe, but it models the laws of physics, gravity, and gas dynamics over billions of years. The scientists can interact with it, tweaking parameters to observe the resultant perturbations. However, we don't know how much of it is imagined by generative AI. And we know that it works because it's based on models that we understand, but we don't know exactly what goes inside. We don't know how it reasons or how it comes to those conclusions. We're observing increasing success in prediction alongside a decreasing intuitive understanding. So our technologies and big data systems mediate the totality of our knowledge, and we see an surge in predictive success. This is what Duran and Formanek, in their work of epistemic capacity, designed the anthropocentric predict method. The algorithm detects patterns, complex correlations between dark matter and the galaxy formation that will remain imperceptible to human cognition. So the model aligns with the data, but we forfeit the why. We are witnessing the ascent on foundation models in astronomy. These models do not merely analyze data, they hallucinate it. However, we must be precise in our phrasing. This means that it's not necessarily a deficit, but a transformation of scientific rationality. We are transforming from a science focused on the teleology of why it happens to what will happen after. When we simulate the universe, so these are the two examples of simulations that we can do. This is the Illustrious project and the Millennium project. We frequently start them as representations, but phenomenologically, they are becoming the primary side of appearance. So we no longer interact with something that is real, even in the cosmos. Even it's no longer something that our data sees, but that we can simulate to understand better. So it's metadata. For many cosmologists, the universe they know is just this, the simulation of the screen, the simulation of the simulation. The real sky is merely a validation set. This exacerbates the temporal mismatch, and the universe operates in a scale of billions of years. Our knowledge operates on millisecond refresh state rates, and we are attempting to capture a deep time process within the framework of a high-velocity trading model. Therefore, in the context of these technological developments, we must interrogate what this implies for cosmology itself, because big data technologies and digital infrastructures are not passive tools for cosmology. They actively shape the modalities by which the universe is studied. We simulate the universe, and this creates data, like new data that we still work on. We're not merely discovering the universe, we're discovering how our code models this universe and how it models under our understanding of it. So we're forced to acknowledge that observation is theory-led. That is that what scientists identify as data already presupposes theoretical framework and interpretive structures. So the concept of theory-ledness posits that observational outcomes are shaped by pre-existing theoretical assumptions and measurements practice, so not merely by raw appearance. In cosmology, this enacted in how data are generated, filtered, and interpreted by implying that scientists are always observing patterns relative to models, so not theory-neutral facts. Cosmology is a science without experiments, just simulations. And it is unique among fundamental sciences because it cannot manipulate its subject. It can only repeat initial conditions, so it cannot intervene. This renders it's structurally observational. It has become computational also. This necessitates a reliance on simulations, a dependence of robustness, and explains why a pattern-based realism dominates. It compensates for the impossibility of experimentation by multiplying models that we also don't understand completely. We understand like the outcome, but we don't understand the black box information behind it. So if an AI discovers a new law of physics within a simulation, one of these ones, a law that perfectly explains the data but is mathematically intelligent to a human subject, do we still accept that as a truth, or do we reject it because it remains opaque to us? Do we accept that it could work even if we understand how it works? Or do we still question if it counts as scientific knowledge, or do we name just justification? So I propose a case study, which is dark matter, not as in itself, but a mental experiment. We can, for starters, problematize its ontological status. So in the classical realistic framework, dark matter is postulated as a substance, and it's an entity like a cloud of wings that await discovery. From a phenomenological analysis, particularly under conditions of radical mediation, dark matter is not a thing we see, but a structural necessity. So it's the correction term that renders the mathematical framework coherent. This is only from a phenomenological point of view. So if we consider the concrete instance of weak gravitational lensing, the map dark matter astronomers observe from distant galaxies, the gravity of the intervening mass distorts the light of these background objects. Yet, these distortions are imperceptible to the human eye. They are inside of the noise of the atmosphere and the instrument. So we only see the dark matter when we aggregate millions of these galaxies and employ an algorithm to extract the pattern. In this context, observation is no longer an act performed by a human subject. We can no longer do this by ourselves, with a telescope, for example, but it is the outcome of a computational process that establishes a signal across noise. So we define what is normal, and we find what is not normal, and then we name it. The dark matter appears only when the code processes the data. We see a shadow, we don't see the substance, we don't see it written dark matter. So, okay, I propose the experiment, which is if we imagine that we had artificial intelligence before we discovered dark matter, how would it find it? So as a pure statistical engine, we feed it telescope data, a galaxy rotation curves, length distortions, but we withhold the theoretical framework of general relativity. We do not provide it with the conceptual label invisible mass. So what would the AI find? We would not detect an invisible substance. Instead, we would identify a systematic discrepancy between the luminous matter and the gravitational effects. It will recognize that the outer edges of galaxies rotate too rapidly for the visible matter to sustain cohesion, and to rectify the mathematics to maintain predictive coherence, it will create the latent variable or a correction term. So it might label it as X or Y or Z or whatever, but it is not a particle. So X is a functional structure required to maintain the integrity of the model. So if dark matter constitutes in the age of big data an epistemic placeholder, it is the name that we would assign the discrepancy between our luminous data and our gravitational models. So if we alter the theoretical framework, for instance, by adopting modified gravity, the dark matter variable might vanish entirely. So if our mode of access is a data pipeline that necessitates dark matter to balance its equations, then dark matter is exactly that, a balancing act in database. It is a ghost in the machine that we mistake for a ghost in the cosmos. The standard cosmological model exhibits remarkable predictive success, yet it expands to everything. We're situated within a scientific paradigm that is predictably powerful yet deeply mysterious. In other words, dark matter is not encountered as a perceptual object, but a structural necessity within a network of observations, models, and computational practices. This places dark matter at the limits of classical empirism, rendering it a revealing case for phenomenological analysis. So, in data-intensive cosmology, this mode of appearance becomes even more explicit. Dark matter functions as a constraint that organizes the space of possible models. It appears as what must be there for the universe to behave as it does, even if its mode of existence remains opaque. In this sense, dark matter is not hidden behind appearances, it is constituted through them, as a pattern that emerges from the interplay between data, algorithms, and theoretical expectations. So because of this, we have to recalibrate objectivity in cosmology. Jeremy Butterfield notes in his work on underdetermination that the available data might be insufficient to decisively confirm a single cosmological interpretation. On the other hand, Leonard Mlodinov advances the idea of model-dependent realism, which holds that we interpret reality through the models that best explain the observations, rather than through the access to direct reality. In this view, theories and models define what counts as an observable pattern. So dark matter would enter the theory as a latent variable optimized for predictive success, and this would short-circuit the epistemic labor through which cosmologists articulated the limits of observation, database standards of recognition, and negotiated the ontological status of observational entities. So what would be lost if it was only seen through big data and AI, generative AI, would not be empirical adequacy, but the problem structure itself. The sense of dark matter as a constant that reshape cosmological reasoning, instrumentation, and model building. So in a sense, a purely algorithmic discovery would abstract away the phenomenology of scientific inquiry, producing correct models without producing the universe as an object of shared epistemic tension and interpretation. In other words, had dark matter been discovered solely through generative big data optimization, cosmology would have retained predictive success while missing the theoretical debates, new instruments, simulation, and epistemic practices that reshaped the field and made us investigate further to fill knowledge gaps. Okay, so objectivity no longer rests on direct observability, but on convergence, because we can't really observe things and we can't really argue on what we observe or what we experience firsthand. So dark matter is considered objective not because it is seen, but because it persists across diverse modes of access in simulation, in lensing data, and in the cosmic microwave background. In this way, big data makes explicit that cosmological knowledge is produced within complex systems, where human cognition, computational processes, and theoretical framework are separately entangled. So we're moving towards that science of appearance. We are studying how the cosmos appears to us through the lens of our own digital creations. And in this way, dark matter is understood phenomenologically, not as a missing substance. It is a manifestation of the ways in which scientific knowledge emerges at the intersection of data, computation, and meaning. And I want to be very clear that I'm not saying that dark matter doesn't exist, but more that it arises from the need to balance an equation. So it is phenomenologically an artifact, how it appears, but ontologically, it has a causal efficiency once encoded in the system. Sorry. So yeah, so I'm going to go to some of the conclusions or final thoughts. We are witnessing a fundamental inversion of the scientific project because the epistemic burden has migrated from justifying the object of perception to justifying the apparatus of inference. So we're no longer verifying the phenomena itself, but rather legitimizing the computational opacity of the system that produces it for us. In other words, scientific validity is no longer contingent on what we see, but on the structural reliability of the algorithm that sees it first. So we have shifted from justifying nature to justifying the data that we get from our instruments. And I would like to conclude with the fact that we must confront, which is that we might be proceeding towards a mode of generative science that goes beyond what we could understand. So maybe the future of cosmology is one in which we are capable only of interpreting outputs, yet no longer capable of recreating the causal chain. So science would like shift completely because we wouldn't understand really what we're studying or how we can use it or how we can explain it. Are we prepared to accept that epistemic opacity is a permanent condition of our knowledge after we start using generative AI and big data? And if so, what is the true ontological role of AI in cosmology? Because the future of science might be about acknowledging that human intuition is a fundamentally low fidelity format. We have been attempting to decode the universe using very simple methods, when in reality, we might not even be able to understand the science that we're trying to explain. So the question is whether we possess the fortitude to utilize this new way of understanding things, or will we continue to delete everything that we might classify as errors, while sacrificing possibilities of new scientific knowledge. Currently, we attempt to rectify anomalies and glitches in our data by inventing new particles, for example, the WIMPs, within the confines of our old forms or our old programs or our old notions of nature and cosmology. So perhaps we're training the next generation of AI in our old pattern and old information that we might need to upgrade and sacrifice our understanding in the way. So we must acknowledge the instrumental efficiency of AI also, which is invaluable for classification tasks and identifying supernova, for example. We face accuracy abnormalities, and our algorithms are becoming so proficient at locating what we expect that the James Webb telescope has required to compel us to see what we did not anticipate. So this compels us to redefine cosmology not merely as a measurement of a physical object, but as an entity we observe through the complex triangulation of human cognition, technology, and data. So this challenges the classical notions of empirical observation and scientific objectivity. By considering these questions, we aim to demonstrate that cosmology today is much about the evolving modalities of big data and scientific justification, and the way that we perceive them. I do want to talk also about the political aspect of this, because if we accept that scientific validity is no longer contingent on what we see, but on the structural reliability of the algorithm that sees it for us, we end up normalizing a architecture of a black box scientific governance. So this transition mirrors a previous shift from a democratic model of accountability, rooted in explanatory transparency and the right to know why, to a technological regime of reliability where authority is secured solely by operational success, such as the standard model functions as a loosey codec that filters out the telescope anomalies to preserve internal coherence. Our political ideologies function as comprehension algorithms that suppress high-fidelity social complexities. So we're establishing an epistemic standardification where the high bandwidth elite, so those who own and control the foundation models, constitute the only subject that capable of perceiving a reality, while the general populace is relegated to the status of low fidelity, mere biological interfaces required to accept outputs without understanding. So we risk engineering a form of automated censorship, that we will be building a digital mirror that's not merely reflect us, but to reform us, mutating our political agency and our perception of dissent until we're no longer knowledge citizens. And I'm almost done. I just want to leave you with a little bit of brain food. So, because I am left with a lot of questions after my research. This is not my main research, but it's a big part of it. So if we're using AI to interpret the universe, and that AI is trained on our current best simulations, we're building a system that is dangerously incestuous. So we just repeat our information with our own information, and we don't end up getting to new information. So we risk entering a state of algorithm solipsism. So a half of kind of mirrors where data reinforce their own biases, so it auto-justifies itself with its own algorithms, and when something doesn't stay within, it fixes it as an error. So like what would have happened with the galaxies had we not intervened. So the anomalies that, for example, the telescope find are only things breaking this loop. There are glitches in the solar system. So the question now is, how can we build a better AI? So one that can really use to understand science and answer all of our questions. So how do we build an AI that is willing to be surprised and willing to not classify just errors as information that we don't want? How do we build a machine that looks at the data, and instead of smoothing it over, says like, oh, this shouldn't be here. What could it be? I don't know. Because if we cannot do that, we no longer study the cosmos. We just look at our own mathematical reflection and auto-justification. So yeah, I think that's it. Thank you very much. I'd love to hear your thoughts or your predictions on what we might do after, and yeah.
Thank you very much, Mariana. And now let's move to the Q&A. We have a question by Niels Saavedra, then Andres, then Sergio. So I'm going to read the one from Niels, and I will ask you to be relatively concrete in answering, because I bet you are going to have a lot of questions. So in a totally different scenario, sorry for the long shift, but do you think that a similar phenomenological and ontological reflection could be applied to climate science simulations? He's thinking about the fact that a hallucination of current artificial intelligence techniques also appears in the lack of meteorological precise data. Any take on this?
So I think that a similar reflection could be applied to climate simulations. I think that it's a kind of applicable to all sciences. No, okay, maybe not to all sciences, but I think that it's applicable to a lot of science studies that we have now, because there's a lot of information that we no longer perceive in a phenomenological sense, because of big data and AI, generative AI. So yeah, I think that yep.
Thank you very much, Mariana. Andres, and then Sergio, please.
Hi, Mariana. Nice to meet you. I was let me clarify my ideas. I was wondering whether you think are you truly convinced that we're not understanding anything in cosmology? That because we do not have experiments, just observations, then we do not grasp the causal structure of the things, that we are all only seeing flukes in the data, but we're not grasping reality in some sense. Is that what you think?
So no, this is mostly like a pre-study, we could say, because we don't have, like, from what I know, we don't yet have a lot of information that is based on generative AI or with data. Like, we still interact a lot with what we see, what we study in cosmology. However, we are implementing a lot of generative AI and big databases for this information. So it's more of like a prediction of what we might start to happen. I'm using a lot of examples that are happening like pretty recent. So it is very early for me to say that this is how it works now. But yeah, so it's mostly a prediction than actual thing right now.
So your talk was about what you think is the aim, the path that cosmology is going to follow. That is this talk about what you think
it's
is going to
about
happen?
AI and big data. So how it will follow and how it's starting to work right now, like how we interact with this big data opacity that is becoming more like difficult for us to understand.
Yeah, well, thank you.
So Sergio, please.
Yep, thank you. Thank you, Mariana, very much for the presentation. First of all, I would like to say that I'm a huge fan of phenomenology, and I like very much also continental philosophy. So I'm glad that you brought it here. So uh, first of all, I have a concern about when you say that we do not know what's going on in the AI environment. I understand that there's always this human input, and in this way, there's always someone that knows how the AI is working. So, but I'm not an expert, so I would like to ask if this is so. Um, Maybe if this is so, the problem would be then not in the AI per se, but on the programmers or the experts of the AI, or even our structure our structure theories, the structure of our theories. Sorry, that's the first comment, and the second one is that Paula insisted us yesterday that the images of the cosmos are not simulations. they are more like some sort of hybrids, right? So I would like to ask you if this is so, there would be a gap in which we, in fact, have experience of the cosmos. So my question to you, I would like to know your opinion, is uh, if there would be a space for doing a phenomenology of the things we of this region of space of experience that we do have about the cosmos, and if so, which would be the advantages or disadvantages, or why would one choose to implement that? Thank you very much.
So I'm not an expert, complete expert on the science of AI. So if someone else knows, feel free to explain. But from what I understand, AI is based on information that is in the big data, so on the internet and how we feed it. So yeah, we have a certain agency on how it works and how it's fed. But we don't really understand how it reasons or how it connects information. So this is the epistemic opacity, like the black box, like the Schrodinger's cat in a box part of AI, which is a very current subject right now in philosophy of science. So yes, I think that's what's the first question. And the second one about the hallucinations. So yeah, we have like a lot of the images that we have from big data are not generated by AI. So they are indeed pictures from satellites that we have in space. However, we do apart simulations of what they could look to try to recreate like so because we can't really do experiments in the cosmos and we can't really recreate a cosmos in our laboratories, we do these kind of simulations to try to understand how they work. So we recreate a universe in a computer system by coding or by implementing all this information that we have. And we try to recreate how we think that they work. So we try to see if they work correctly or not. And then if they don't, we try to fill out our knowledge gaps. This is from what I understand. Again, if there's someone else who is an expert in the room, feel free to explain further. But this is from my research and what I understood.
Thank you, Mariana. Before moving to the next question, let me make a follow-up on your comment. I think artificial intelligence is one of the ways in which we manage big data, which is characterized like large amounts of information, but also from a different varieties of information gathered at a very high speed. And then it doesn't necessarily mean that it's going to be related to internet or other like informational phenomena in particular. So in the case of astronomy, it's artificial intelligence is applied to manage the large amounts of data that are gathered by the observatories. And so that might be the way in which it's playing the relation, but it's not necessarily, as you were mentioning, not necessarily is the only way in which large amounts of information are managed in the history of astronomy, at least. So let's move to Lisa, please.
Yes. So thank you, Marina, for your presentation. I guess my question is more about ontology of science and maybe methodology of science, because you're talking about epistemic opacity. So if we accept, do you think that if we accept epistemic opacity and stop asking the AI to understand, well, asking to understand what's going on in the AI, we're kind of just abandoning the core mission of physics, and we're complying to blind empiricism. So how is this? Yeah.
Sorry. So yeah, I did want to talk more about this. I did not think that I would have the time, but it's about the work regarding Judy Pearl. So the letter of causation. So we are not abandoning causality. We are outsourcing the computational trace. So we move from epistemology of understanding to a sort of epistemology of control in his theory. So in the past, understanding means so like tracing like A to B, like Newton deriving from the orbit of the moon. So it's like a luxury of low data science. But in a high dimensional system like the cosmos, our human intuition doesn't really do anything. So if a neural network identifies a correlation that predicts the expansion rate with 99% accuracy, we cannot open the black box to see the math and like how it works because we wouldn't understand it. So we haven't lost causality. So we're simply lost in the narrative of causality. So this is all Judy Pearl. If you want the name, I can write it down. So we have the causal link still exists in the maths of machine. It is just inaccessible to our biological consciousness. So to reject this because we can't feel the logic is to commit what Duran and Frommerich call the anthropocenic predicament. It is inciting that the universe must be small enough for our minds to contain. So I would argue that we're not abandoning the classical web science, but we're upgrading the definition from the construction of intelligible narratives to the creation of robust computational contrast. Wait, I can write the name of here. Okay, I'll put it on the chat. I don't know. I hope that answered your question.
Yes, she said yes in the chat. So now I think it's my turn, and and now we got Judy Pearl in the chat. Mariana, I am a bit confused about the extension of the damage that you claim artificial intelligence might be able to do in cosmology. In particular, one of the points at least is the one of understanding, because I think I'm not alone in this. There is Emily Sullivan, Andres Paez, and myself. I think we are all in agreement on the saying that in these cases, because astronomy has a long history using heavy technological dependence in interpreting and getting the observational outcomes, right? So our claim is often that we can get some understanding, but only by using the theories that we have, that we think that are entrenched and that we think that are justified. So those theories are actually going to reinforce the observational outcomes that we get, and in a sense help us dealing with the epistemic opacity consequences at the level of justification that we might have. And so in that sense, we think that there is some sort of a strong understanding that we can get, even if it's not related to causal explanations only given by the artificial intelligence, but because of the combination of the results and the theoretical frameworks that we are working within. Also, say that that's not your take. Say that you don't want to combine theoretical commitments with the observational outcomes that are coming from a very opaque processes and so on and so forth. We still can say that we can get some theoretical understanding of the phenomenon, like very abstract, like the mathematicians or the logicians get scientific understanding of their disciplines, even if your claim is that observation is in a sense forbidden, like to be justified for us. We can still say that we have a theoretical understanding of the phenomena that we are describing, even if the observation is not pure and we cannot assess the level of justification that we have to endorse towards it. What is your take on this?
So this is like very interesting. This is what motivated me to research more in cosmology, because I thought that was very interesting. So my take in this presentation is more a phenomenological one. So our direct intuition of things. So how we don't understand them as an evidence firsthand. Like I understand that we can understand them. For example, if we interpret these data, if we're like scientists that understand, like, yeah, if we study them, I understand that we can understand that. But my take is more a phenomenological concern of how our first intuitions are no longer what makes this type of science reliable. Like as in classical science, we could observe something like your gravity, for example, we can observe gravity in a more classical sense and understand it, and then be sure that it's true. This is my take. I do think that it's very interesting. I'm still researching on this. This is still a work in progress, but thank you.
So let me make a follow-up on that answer, because it seems to me that what you could be saying is either of two things. On the one hand, that actually cosmology is not observational at all, and it's only about abstracta or unobservables. And we now realize this because of the problems that are coming with artificial intelligence in general, but we had these problems since the beginning. Or you are saying that we used to have a grasp, like an observational grasp of phenomena, and now because we are mediating that observational grasp with artificial intelligence, we are going to lose it. If it's the first one, that's very weird to me to say that observational cosmology is not observational. If it's the second one, it's very tricky because initially, like all of the observations were not mediated by artificial intelligence as we know it right now, but they were, of course, mediated by algorithmic cleanance of the data, gathering of the data. The pictures that we see are often like black and white maps that are integrated by automatic algorithms. And then they are colorized, not because we think that's are the colors of the space, but because they have a cognitive function, or at least to make it clear, like the distinctions, they have like a pragmatic function in that sense. And so it's not so different, the mediation now. Maybe it's more opaque, but it has been opaque enough since the beginning. So is there any of these two takes, the one that you are defending?
I guess it resembles more the second one. I don't know if I'm allowed to do this, but I do have a question on your the second part in what you said about how these systems have been opaque since the beginning. Like, again, this is research in progress. I don't know like everything, but does that mean that like we have been so like what I'm saying is that these things have not been things that we experience firsthand. So phenomenologically speaking, it's not things that we can see directly. So yeah, that's exactly what I'm saying, that these are not observations that we can make in a classical sense. But then in this okay, sorry, I need to so in the classical sense, how do we make cosmology a science of observation when it's like seen through these data sets that are not first-hand observations? Like, how would you argue that that would work in a phenomenological sense? Like, how can we? Yeah, sorry.
Because it's technologically mediated observation, but it's technologically mediated observation almost in all sciences, right? So the only thing that is happening here is that we are very much aware of how much dependence we have and how many steps there are needed in between. So before you get the picture that you see in NASA's website, you have to get the gathering of different information, which is basic building of big databases, and then you get filtering, integration, and then you get the measurements, and then you integrate those measurements into a black and white map, and then after that you colorize them. So yeah, we are building observation in the same way in which we build observation in other disciplines, but maybe it takes longer time, or it takes longer participants, larger amount of participants to get this things that we call observational outcomes. But it doesn't mean that they are not almost the same type of mediation that other disciplines have when they are calling mediated observation outcomes or something like that.
Okay, so my take is more than that it becomes more opaque the farther away we see this information. So because we interact with these observations through a mediated model. So like through the observations that we don't make ourselves, but another system that we build. So we risk that it's auto-justifies itself because we're building the means in which we're interacting with this data. So like my main take is that we risk that it becomes an auto-justifying science. Not necessarily now, but like in the future, we keep using databases and generative AI to interact more, like because it's already a technical way that we interact with these observations, with this data. It risks to become just information over information that we no longer understand. So that's
Thank
my
you,
main-
Mariana. Yes, thank you very much. Andres has a question, and if you have a question and you are on YouTube, just type it in the chat. If you are here, just go to the reaction buttons and raise your hand. Andres?
Sorry, I was having some trouble. Yeah, Mariana. The first question is about is I think a follow up on Maria's, because I am concerned that of the limits of what you're diagnosing, because there is another sense in which I think we can get understanding in cosmology, even though it is now algorithmically mediated, and that is counterfactual understanding. If you look upon some websites, you can find some models of the universe that where you change the amount of dark matter, dark energy, you get a totally different universe, and we can understand this. So that was the first question is like, what do you take as understanding? And the other question is, wouldn't it be then that our phenomenological frameworks are old? I mean, if we don't allow observation, technologically mediated observation, as Maria said, we lose a lot of things that we now think that is observation, not only in physics, but also in biology, in chemistry, in many other sciences. Also, I was concerned about the epistemic capacity that you're mentioning here. I am concerned that you're diagnosing essential opacity where there is only some epistemic capacity. I mean, there are cases where astronomers have argued, that have assumed, that have affirmed that they were actually seeing an artifact of the measurement instrument, but they are capable of identifying it. And so there is like no support to call an essential opacity thesis just partial essential opacity. Moreover, the way in which robustness works is precisely to make the inference independent of the premises that you have. So if you have different observational data, both interpreted by different programs, then they are no longer dependent on those programs. That's the way robustness works. And robustness is working not just at the level of the different programs, but also inside the very programs. Even though now we're moving to a more technologically mediated cosmology, I do not think that we're moving to a riskier cosmology, nor a cosmology where we are not grasping the objects that we're seeing in space. In fact, the cosmic microwave background was discovered even before we had algorithms to filter the data. The filter were made, were human made. There were people that were positing novel models about what were the possible flukes that we could have here. I mean, I am concerned about the scope of your critique. What would you say on this?
So first for the phenomenological, yeah, maybe I wasn't very clear. I didn't expand on it, But yeah, I'm mostly critiquing phenomenology in its science regard in the second or third part. Wait, I'll find it. So yeah, no, I agree that phenomenology is no longer able to explain or question our interpretation and our interaction of world phenomena. So I agree with this. And in this second part about robustness, I am mostly using Marie Gauguin theory. So she is arguing that sorry. I want to just make sure that I'm saying it correctly. So she argues that scientific objects are not merely given, that they constitute, and in the okay, so she argues that the scientific obsession over robustness uses a logical trap, so that robustness is only valuable if the lines of evidence are truly independent. But in modern cosmology, they are not. And if we run simulations,
But why are they not? Why are they not? Because we have data from, for example, photons, neutrinos, gravitational waves, and all these forms of evidence are gathered by different instruments. We have LIGO, we have Super Kamiokande, we have, for example, Hawk, and they work in causally very different ways. In which ways are these not truly independent?
Okay, so this is not what I researched for this project. I can leave you the link for the article that I based this off. So it's here.
And I think that we would appreciate if you get like a general final thought, Mariana. We are running a bit late, partly because of my question. And before you answer to Andres, I would mention also what Sergio is saying, and he thinks that would also depend on how one takes phenomenology, because it is not reduced to merely sensorial captation. So maybe that helps for you to make a final comment.
A final comment? Sorry, I didn't.
Yeah, I thought that you were still replying to Andres and that you want to say something in the end so we can close the session.
Well, I do want to leave the link that I left in the group for Marie Gauguin. I think that her work is very interesting. And again, I'm not a cosmologist. I'm mostly doing the work on epistemic capacity and big data and how it would reflect. So yeah, I will leave the link.
Thank you very much, Mariana, and please give her a round of applause. Now we are going to move to the break, and in order for it to not be only 5 minutes long, so we are going to come back in 10 minutes. So here in Mexico at noon plus 5 minutes, and wherever you are, just similar time. So thank you, Mariana.
Thank you.
And see you in 10 more minutes. Alessandro,